to the second video of the 19th chapter of the Crystal Clear Electronics curriculum. With Ádám, we will continue our presentation of EEPROM memories. We are about to get to a practical application that everyone is waiting for. But before that, it is important to talk about the durability of non-volatile memories.
If you have bought or are flirting with the idea of buying an SSD, you have probably come across the TBW, terabytes written value. This number shows how many terabytes of data you can write to the SSD, so to the flash memory, in its lifetime. For example, for a 1 terabyte SSD, you can see that you can write 600 terabytes to it over its lifetime. It basically means that you can erase and write each block 600 times. Even though this could take many years under normal usage, we should still expect a finite lifetime from our memory. But now, let's return to the world of EEPROMs. Previously, I've managed to illustrate how many things an EEPROM can be used for. The limit is really only our imagination. But when using an EEPROM, it is important to keep some things in mind. Most importantly, our memory has a finite erase-write cycle, so if we want to get the most out of it, we have to make sure to only write if it is necessary. What constitutes as necessary depends on the memory and the application. With the EEPROM in the Atmega 16A, we have a guaranteed 100,000 cycles. Let's look at the relevant figure of the curriculum. You can see that both axes of the diagram are logarithmic in scale. This is because there are several orders of magnitude of difference between each case, so we can't show them at the same time on a standard linear scale. If we would store the value of a variable every second, we would use up our memory in little more than a day, as there are 86,400 seconds in a day. However, if we only write a value once every 315 seconds, our EEPROM is guaranteed to last more than a year. It is similarly predictable that it would take exactly a week to perform 100,000 writes to our EEPROM at 6 writes per second, and a month at 26 writes per second. So the EEPROMs are not ideal for storing fast-changing values, and it doesn't make sense to erase and write them frequently, since their main purpose is retaining data without a power supply, meaning when the device is powered off.
To increase the lifespan of the memory, we have several techniques. The most obvious is avoiding unnecessary writes by only writing a value if it differs from the currently stored value. This means that before writing anything, we read the contents of the memory, compare it to the new value, and we only write if they don't match. This method increases write time in cases where it is actually required, but decreases it where no real write operation is necessary. Therefore, this is not the method to use where the values are guaranteed to be different every time, for example, counting.
Another technique is if we know when our device will switch off, we can write every important value that we were storing in RAM to EEPROM before switching off, and on the next power-up, we load them back to RAM. We can build a circuit that detects power supply failure easily, but we have to be careful that during the whole EEPROM write process, the supply voltage of the microcontroller and the EEPROM must stay above the level specified in the datasheet. If the supply voltage is lower than the limit, the behavior of the microcontroller is undefined, and we may write incorrect data to the EEPROM, or the whole write process may fail.
A third option can be used if we only need a small portion of the available memory, which is usually true. Suppose we have an EEPROM with 512 bytes, but we only need 30 bytes to store our data. The EEPROM guarantees 100,000 erased write cycles, after which we would have 30 bytes nearing the end of its lifespan and 482 bytes that have never been used and still have at least 100,000 cycles left. it would be foolish not to use this memory.
In practice, we try to evenly distribute the wear of bytes across the whole area of the memory, so at every write we are using a different address. This process is called wear leveling. We segment the memory to 30-byte blocks, 17 of them in total, and we always write to the next block, looping back to the beginning when reaching the end. We are not done yet, because we need to know when turning on which block contains the most recent data and what address we need to write next. We could store this in a pointer stored in EEPROM. The naive solution is to store it at a fixed address and at power on read the address of the most recent block from there. But this would get us nowhere, as this pointer has to be updated every time we do an EEPROM write, so that memory area would wear out after the guaranteed 100,000 writes, not giving us any benefit from moving the data around in memory.
Mint egyszerű esetben, ha minden adatot ugyanarra a memória címre írunk. Erre az a megoldás.
The solution is not to use a pointer, but to mark the next block to be used for writing with a special pattern. Because reading the EEPROM does not cause any kind of wear, we can create an algorithm which reads the entire memory region after powering on the device looking for the pattern. If found, the data should be written there next time. If not found, we should use the beginning of the memory, as it is probably the first time using the device. The special pattern can be the 0xFF byte, which signifies an empty byte in EEPROM. We only have to make sure to store data in such a way that 0xFF does not occur in it.
A 0xFF ne jelentsen más értelmes értéket. Tehát egy írási folyamat.
A write process then looks like this. Fill the current block with useful data and erase the next block, fill it with 0xFF.
Így minden írás során.
This way, at every write, we are writing 2 blocks, so we only get 8.5 times as much lifetime from our 512-byte memory if talking about 30-byte blocks, instead of 17 times as much.
Ha mind a két módszert alkalmazzuk,
If we use both methods at the same time, we can increase the lifespan of our EEPROM considerably. Of course, if we are storing values that rarely change, 1 to 2 times a day, such as calibration values or control parameters, there is probably no need to use these methods and to implement such lifetime extension functions. Now let's look at a practical example from the lesson.
a lépésszámláló feladata
The job of a pedometer is to count the steps of the person wearing it and store the value until the user resets it to 0 using the reset button.
a lépésszámláló
A pedometer also has to store the total steps counted since manufacturing.
számláló akkumulátorról működik.
The device works from battery power and has a 256-byte EEPROM with 100,000 guaranteed write cycles.
Az aktuális lépésszámot
The current step count is stored as a 24-bit integer, and the total number of steps is stored as a 32-bit integer. We want to count steps during the day when the user is awake, which is about 14 hours.
nagyjából 14 óra.
Calculate the guaranteed lifespan of the EEPROM in the simple case, with only storing data at power off and using the full memory range as well. For simplicity, assume that there is at least half a second between 2 steps.
I suggest you stop the video here and try to calculate the 3 cases. We'll give you time to find the pause button.
Megállítottad?
Have you stopped it? I see you haven't. Give it a try before you look at the solution. And then we will continue with the solution 3, 2, 1.
Akkor először
Let's first look at the
nézzük meg
total
a
number of
frissített
steps.
lépésszámot. A reset gomb megnyomása
When pushing the reset button, we have to add the current steps to the total number of steps
kell adni az aktuális lépésszámot.
and then set the current step counter to 0.
Az átlag
The average user is interested in how many steps he or she has taken during the day, so we can assume the device will be reset once every day. This means we will write the total step count in EEPROM once a day, which is such a low frequency, we can simply allocate 4 bytes to it. The lifespan of those 4 bytes is
ennek a 32 bitnek az élettartama, így
24 hours divided by 1 period per day, multiplied by 100,000 cycles equals 274 years.
274 évet jelent. Nézzük most.
Now let's look at the simplest way to save the data. This time, we store every change in EEPROM.
Ez azt jelenti,
This means that after every step, that is every 0.5 seconds, we increase the value in EEPROM.
időközönként írjuk a memóriát. Ez azt jelenti, hogy az
The lifetime of that memory region is half a second multiplied by the number of 100,000 cycles, which is 13.89 hours,
felfele kerekítve
rounded up to 14 hours of usage, which is at most 7 days if we assume only 2 hours every day.
7 nap. Nem biztos, hogy ezt az
I'm not sure many people would buy it with that written on the box.
Let's add a new feature to our step counter. The pedometer senses the steps after idling and turns on, and after a long time without any steps, for example when the user is sitting, it switches off to save battery power. Every time it turns on, it reads the current steps from the EEPROM, and during operation it increases this counter in RAM. Before turning off, it updates the value in the EEPROM. Suppose that the user is health conscious and moves for 5 minutes every 15 minutes. This results in the device turning on 56 times during the 14-hour awake period,
Utóbbi igazából lényegtelen, lehetne több vagy kevesebb is. Ebből az következik, hogy
which means 56 EEPROM writes each day.
így a teljes élettartam a
T is 24 hours divided by 56 and multiplied by 100,000 write cycles is 4.89 years, so roughly about 5 years.
ezzel a megoldással
With this solution, our device can work for almost 5 years, which is a lot better than 1 week.
hozzásabb érték.
Az utolsó esetben
In the last case, let's examine what kind of lifespan can be achieved by using the full memory.
tudunk elérni. A lépésszámot
We are storing the step count on 24 bits, that is 3 bytes,
a 200
so we can partition the remaining 252 bytes. Remember, we have allocated 4 bytes to the total steps into 84 blocks.
4 blokkra oszthatjuk fel. Mivel minden
Since we write 2 blocks during each write, one to store the data and one to store the pattern to find the fresh data in memory,
2 írás
we perform 2 write operations, so the lifetime should be 42 times bigger than in the previous case,
mint az előző megvalósítás,
which is about 205 years.
205 évet.
You can see from these examples that you have to be careful and think about the application when using EEPROMs if you want a good lifetime. And you can also see that with a few tricks, the lifetime can be greatly increased.
Ezzel el is
This brings us to the end of the second video of Chapter 19 of the Crystal Clear Electronics curriculum,
remélem hasznos.
and I hope you found the information here useful.
A következő videó
The next video will be the final video on the topic of non-volatile memories. We'll look at a practical example of using the EEPROM of the ATmega16A microcontroller. Stay tuned for more. Bye!
Bye!